Locked rotor indicating code letter is a designation found on the nameplate of an alternating current motor. This letter provides information about the motor's locked rotor current, which is the current the motor draws when it's initially energized but the rotor is not yet turning. It's an important parameter for determining the proper size of overcurrent protection devices, such as fuses or circuit breakers, and for assessing the impact of motor starting on the electrical power system. The locked rotor current is typically much higher than the motor's full load current, often 6 to 10 times higher, or even more. This inrush of current can cause voltage dips and potentially trip circuit breakers if not properly accounted for. The code letter helps engineers and electricians select appropriate protection devices that can handle this temporary high current without nuisance tripping, while still providing adequate protection against sustained overloads or short circuits. The code letter corresponds to a range of locked rotor kilovolt amperes per horsepower. A higher code letter indicates a higher locked rotor current per horsepower. The National Electrical Code, or NEC, provides tables that relate these code letters to specific kilovolt amperes per horsepower ranges. Using this information, one can calculate the expected locked rotor current for a given motor size. The information is crucial for motor installation and protection. For instance, when selecting the size of a circuit breaker or fuse for a motor circuit, the NEC specifies that the overcurrent protection device must be sized based on the motor's full load current and the locked rotor indicating code letter. This ensures that the device can handle the inrush current during motor starting without tripping, but will still trip under overload or short circuit conditions. The code letter is also important when assessing the impact of motor starting on the power system. Large motors with high locked rotor currents can cause significant voltage dips when they start. This can affect the operation of other equipment connected to the same power system. Knowing the locked rotor indicating code letter allows engineers to estimate the voltage dip and take steps to mitigate it, such as using reduced voltage starters or increasing the capacity of the power system. The locked rotor indicating code letter is typically located on the motor nameplate, along with other important motor data such as horsepower, voltage, full load amps, and speed. It's usually represented by a single letter, such as A, B, C, D, E, F, G, H, J, K, L, M, N, P, R, S, T, U, or V. Each letter corresponds to a specific range of kilovolt amperes per horsepower, as defined in the NEC table 430.7. The higher the letter is in the alphabet, the higher the locked rotor current per horsepower is. To determine the locked rotor current, one must find the code letter on the motor nameplate. Then refer to the NEC table 430.7 and find the corresponding kilovolt amperes per horsepower range. Multiply the motor's horsepower by the kilovolt amperes per horsepower value from the table to get the total kilovolt amperes. Convert the kilovolt amperes to amps using the appropriate voltage for the motor. Using the formula, amps equals kilovolt amperes times 1000 divided by the voltage and the square root of 3 for three-phase systems. For example, consider a three-phase motor rated at 10 horsepower, 480 volts, with a code letter of G. According to NEC table 430.7, code letter G corresponds to a range of 6.3 to 7.9 kilovolt amperes per horsepower. One could take the maximum value of 7.9, multiplying 10 horsepower by 7.9 kilovolt amperes per horsepower yields 70.9 kilovolt amperes. To find the locked rotor current, divide 70.9 kilovolt amperes times 1000 by 480 volts times the square root of 3, resulting in approximately 85.2 amps. This value can then be used to select the appropriate overcurrent protection device for the motor circuit. The locked rotor indicating code letter is an essential piece of information for ensuring the safe and reliable operation of alternating current motors. It is used to select proper overcurrent protection, assess the impact of motor starting on the power system, and prevent nuisance tripping of circuit breakers.